Good. Okay, hello, welcome to the next Tuesday seminar at the Astronomical Observatory at the University of Warsaw. And today our speaker is Nadia Blagorodnova from Barcelona. Nadia has done her, she studied in Barcelona, but she did her PhD in Cambridge, where we happened to work together on Gaia and transients and supernovae stuff. And then she did her postdoc at Caltech, and then in Radboud, and now she's a distinguished fellow at the University of Barcelona. And Nadia is working on transients still, but she moved to a closer types of transients, Luminous Red Novae. Nadia, please.
Yeah, thank you for the introduction, Bukas. Yeah, so it's a pleasure to be with you. I wish I could be in person, but I had some professional commitments, so I had to be here physically. So thank you for being here virtually. So yeah, today we'll talk about the common envelope phase in the binary stellar evolution, and what can we learn from this phase using observations of this type of transients that we call luminous red nova. And I think there is a strong connection of Polish universities with this type of transients, so I'm actually very happy to present them. So looking at our sun, we can think that, well, single stars are the norm, and this actually can be the case, but for lower mass systems. So recent studies show that, for example, the fraction of stars with nearby companions increases with the mass of the primary star. So for something like our sun, it's like 20% of less have a companion, but for more massive systems, which are kind of exciting because they explode or they create gravitational wave sources, nearly most of them have a companion or even more than one, because this fraction can go above 1. So that means that massive stars like to be in binaries or in triple systems, and they do also interact with each other. And we like these interactions very much because they create some of the most exciting astrophysical phenomena that we like to study. For example, close binary interactions create different type of supernova progenitors, such as like Novian type 1a progenitors, but also stripped core collapse supernova which interact with the circumstellar medium, or these giant eruptions of luminous pro-variable stars. But not only that, if one of these stars becomes a black hole or a neutron star, for example, they also can create gravitational wave sources or, for example, these X-ray binaries. And the stripped cores of these binary stars that have been stripped by the companion likely also played a crucial role in reionizing the early time universe, or, for example, in ionizing the shells of these ejected layers in planetary nebula. So we really care about binary interactions. So how these binaries interact? And this was one of the key papers proposed by Paczynski, well, among others, where he postulated the existence of a phase which he called the common envelope. So basically, was one of the stars, one of the star companion would expand beyond the Lagrange point. It will kind of engulf the companion, so that then these stars would spiral into each other, and then the transfer of energy, of the angular momentum from the orbit into the envelope will help release the envelope, creating a much shorter system. So that was proposed, the creation channel of this binary, for example, the V471 tau, which likely started with a initial period of about 10 years, but right now it's a very tight system of like half a day orbit. So then he also mentioned that if we would observe binary stars in the core of a planetary nebula, that will also be the proof. And nowadays, current surveys have detected about 20% of compact binary stars in the cores of planetary nebula, suggesting that this is a viable mechanism. This is kind of the remains of a full common envelope ejection. So let's just think back about what this happens. So one star evolves with time. So here you see the lifetime of the star in years, and here you have the radius. So during the main sequence, the radius of the stars is fairly constant. But once the hydrogen is exhausted in the core, hydrogen burning, then basically the burning moves into a layer, into a shell. And this shell gets very hot. So basically this contributes to kind of further expand the star. until reaching the helium ignition point. But this phase goes really, really quickly. So the star increases about an order of magnitude its radius in a very, very short period of time. So then if there was a companion nearby in some distance here in between, the main sequence radius and the helium ignition, likely this star will grow so fast that it will expand beyond its Roche lobe, and it will start transferring mass through this inner Lagrange point 1. And basically, if more mass is transferred, all the Lagrange potential will be filled, and the star will start losing mass. So this is kind of the key steps in this common envelope evolution. So at a starting point, we need to understand how this primary star evolves and when it will reach the initial point of Roche lobe overflow, and it will start transferring mass. So then the second point is this slow mass transfer, which starts very stably. It's a very slow mass transfer, but then it exponentially increases until this point that when the gas starts to escape the system, and this happens through the Lagrange point number 2. So basically, this is kind of a tail. And if more of this potential is filled, then L3 will be also a point where the system will start losing mass. But losing mass, it's also losing angular momentum. So basically, in a matter of a few years, as we will see, the system will actually just coalesce. This co-rotation will stop. So normally these closed systems are kind of locked together, so they are like rotating, facing each other. But when one of the stars expands so quickly, so fast, basically the system kind of stops co-rotating, and basically the small star will enter and spiral into the envelope of the primary star. So then the common envelope will be born. And when enough angular momentum is transferred to the envelope, it really depends on the evolutionary stage of that star, that either, there is not enough angular momentum, we just eject a little bit of mass and then we will merge the system, or there is enough angular momentum and basically the whole envelope will be ejected, such in this planetary nebula, leaving a really compact binary system. So then, what are the steps? Then this final ejection will be observed as one of these luminous red nova transients. So here in this beautiful picture, you see this red star is the Luminous Red Nova, V838MON, in our own galaxy. It was in a young stellar cluster, and what you see around it is a beautiful light echo of the outburst in the surrounding gas. So observational astronomers like me, we can use facilities such as, for example, the Zwicky transient facility, or now the Black Gem facility that just had a first light and a press release, I think, last week. So then we can image the sky repeatedly in search for this kind of luminous red nova in nearby galaxies. Then we can trace, their evolution in the light curves in different colors, and we can also follow up with spectroscopy in several points. And we also hope that LSST will start soon, which provide even more of these transients at a larger distances. So the Rosetta Stone of all stellar mergers and luminous red nova was this object, V1309 SCO, which was published by Thailenda from Doron Observatory. So initially it was identified in Ogle data as a microlensing event, but then they saw that it did not follow the typical pattern, so decided to analyze further this system. And what they saw is that, for example, before this outburst in 2007, 2008, there was a huge scatter in the light curve, which did not agree with kind of like really good precision in the Ogle data. So what they discovered is actually that was an eclipsing binary where they could compute the period over the years of observations from the Ogle survey. And what they saw is that this period was exponentially decreasing, very close to this outburst. So finally, they saw the outburst in 2008, and the system did not show any periodicity anymore. So by using these eclipses and other data from the progenitor system, they could derive the masses. It was a low mass 1.5 primary with a low mass companion that actually merged. So this is the most strong evidence of a stellar merger that we have in our own galaxy. So this system is here, it's V1309 SCO, and if we put in context Luminous Red Nova into other astrophysical transients, we see that this is the timescales. It lasted relatively little, like just a few tens of days, and its peak luminosity was even below classical novae. But other objects that display similar spectroscopic and some photometric characteristics to this object can be placed in this kind of banana shape, and it's between core collapse supernova and classical nova. So we call some of these luminous red nova also intermediate luminosity transients, because they are kind of sitting in between supernova and nova. And for a survey like, for example, ZTF, we can kind of see them at their peak luminosity up to 100 megaparsecs. So this is kind of a very local universe transient in contrast with superluminous supernova, for example, or even tidal disruption events, which can be seen from much further away. So here you can see a sample of light curves for this luminous red nova. And as you can see, there's a huge spread in the luminosities that we will discuss later. But there is two main features in their light curves that are repeated over many objects, and is that they have a really kind of quick blue, it's called blue peak because it has blue colors, and then they have a much slower red peak where they display much cooler temperatures. So if we look at the spectra of these objects, so this is the wavelength and the flux, and this is a zoom in into the H-alpha profile, we can see that around this blue peak is mostly a hot continuum with strongly ionized Balmer lines corresponding to mostly ionized hydrogen, which is scattered through a fully ionized photosphere. That means that all the outburst is very hot and fully ionized, but with time, this spectrum becomes redder and redder. So at the beginning of this red peak, it becomes kind of a G-type star, and towards the end, it really becomes like an M-K type star. And also the kind of the center of the line profile migrates towards blue shifted velocities, meaning that there is not only cooling in the photosphere, which makes the star appear colder and these molecular bands appear, but also there is dust formation. And it's because if there is emission from hydrogen that's like coming towards us and is receding from us, and there is dust formation, we don't see the receding tail. So we only will see the blue shifted part, and that's what we see in this profile. So basically, this the description is in agreement of a shell of very hot gas, heated gas that was ejected, but is progressively cooling down. So luminous red nova it's kind of a really bad name because it's not a nova, nothing has burned, nothing has exploded there. It's just kind of a peaceful ejection of the common envelope of this binary system. So then, how stable this mass transfer is, and then how do we know if that system in particular ended up in a merger or in a fully ejected envelope. So for that, we employ this common envelope formalism, which is a very simplified formula, which says that to unbind the envelope of the primary star, we need to inject kind of the orbital energy of this binary. Of course, the orbital energy of the binary depends on the two stars and their initial and final separation. And this is done with a certain efficiency, which is called the alpha parameter, which goes from 0. So like none of the orbital energy was transformed into unbinding the envelope, or 1, which means that everything has been transferred. But also depends on these lambda parameters, which encompasses the envelope structure. So this parameter will be different for a main sequence star, a yellow giant, or a red supergiant. So then how we can use observations to study where this instability is. So if we discover a luminous red nova, one of the things that we can do if we are lucky and there is archival data is actually to go back in time and look what kind of star was there, and then make sure that that same star disappears. So if we see it disappear, then that means that that was a progenitor. And using this archival data, we can actually model the properties of the star, such as the temperature, the luminosity, the radius of the progenitor star, and place it in kind of an evolutionary track to estimate which mass that star was. And for this luminous red nova in particular, which actually happened in M101, we can see that it's located here. So if you're familiar with HR diagrams, like the main sequence of a star, it's kind of this little bit over here. And then the stars becomes this really fast growing radius that I showed before into becoming a red giant. So this star, it's in fact located in what we call the Hertzsprung gap. It's called the Hertzsprung gap because there are barely any stars there. And the reason is because they cross really fast this Hertzsprung gap. For example, this arrow shows that in 3,000 years, the star would have crossed this distance, in the Hertzsprung gap. And 3,000 years in a life of a star that lived for millions of years, it's nothing. So it's a very, very quick increase, which is in agreement to this diagram that I showed before. So then if there is a companion here, then it will very likely initiate an unstable mass transfer. So some of the recent works actually explored where it's the regime where the stars will fully eject their envelopes or they will merge. So for example, for Jakub Klęczki, so I think he was a student in the Warsaw Observatory as well. So he explored, for example, for the metallicity of SMC, where the full common envelope ejections are. And basically the result was that these massive stars only could eject all the envelope and leave a compact binary in the regime of red supergiant. So if any companions which are located kind of in distances of a main sequence or Hertzsprung gap, they would necessarily end up in a merger. So a similar work also explored for a 30 solar mass primary, what would happen if it would have a companion, a black hole of different masses from 0 to 20, located at different separations, which is reflected here in the orbital period. So you can see all kind of nearby orbital periods end up in a merger, and only a fraction will end up in ejection, and some it's like just stable mass transfer. And this is for this alpha efficiency parameter 1. If we assume not all the energy from the binary was transformed into ejecting the envelope, we can see that the region of the full ejection is shrinking. And this has a very important influence on the rates that we can compute for example, gravitational wave sources, because in this case, we want that to create a double binary black hole, we necessarily need to eject all the envelope so that this binary survives. So one of the things that we explored is what happens when you initiate this mass transfer. So this was the location of another progenitor of Luminous Red Nova that we found recently. That was an eruption in 2018. And we can see that if we use a single stellar evolution tracks, the progenitor would be in agreement with about an 11 solar mass star. But if we treat it as a binary and model this binary mesa, for example, what we see is that the mass transfer itself causes a huge drop in the luminosity of the primary star, so that masses between 12 and 16 would be more in agreement with the primary star mass. Then, when the primary starts overfilling its Roshlop, as I mentioned, it's kind of called a semi-stable mass transfer because it starts very slowly, but then this process becomes kind of a runaway. So it starts very steeply to go to very high values. And the effect is that as long as you have this mass loss from the system, your period will decrease. So basically, in these final stages, we spend about centuries transferring mass in that system, so it's not immediate. But after some centuries, the system basically became so full of gas that it started to lose mass from this L2, and then the merger happened really quickly. So what happens? So when you start losing mass from this L2, for example, this mass loss starts to kind of like wrap up around the system, and it also self-shocks. So the matter kind of slows down, and then the new matter crashes into this, so we can increase kind of the temperature in these shocks. And there is a certain emission from this newly formed kind of decretion disk or mass loss disk that is formed around the system. So this approach was used to actually model the period change also for this system that I mentioned before. So as you can see here, there is this mass loss from the Lagrange point number 2 in the top. And here you have the visualization of this binary. So in this case, we believe that we could see the system nearly edge on. And because of this mass transfer, it was kind of obscuring this little star. So basically, towards the end, the signal transformed from a double kind of hump eclipsing binary profile into a single hump. And it's that because this mass was kind of obscuring this little binary component, so we couldn't see it anymore. So we really look forward discovering more of these systems where we can see exactly how the period changes to relate it to mass loss in the system. And we actually see evidence that this is the case. If we look at luminous red nova in nearby galaxies, for example, this is one in 2015 in M31, and this is the one in M101, we see that several years actually before the main outburst, there is evidence of kind of a change in the luminosity of the progenitor system. So this was the progenitor in the HST band, and we see that it's slowly growing up. Then there is a dip. It's maybe due to dust formation in the system, and then like a small up, and then there is the outburst. And the same happened here. About 5 years before the main outburst, the system started to brighten gradually until a quick outburst happened. So what we learned from this luminous red nova, it's likely in this case, the system was in this semi-stable mass transfer, but likely around here is when the system started losing copious mass from the L2, and that really helped to suck the angular momentum out of the system. So then it coalesced in a matter of a few years. So then the idea, for example, of a project that we did with a student was to look for which systems, for example, from Gaia data, showed some increase in, a slow increase in luminosity. So that would point to a likely luminous red nova coming in the next years. So we look for kind of yellow giants and supergiants kind of located between the main sequence and the red giant star branch. And he analyzed the time variability of these sources. And we see, like, unfortunately, many of them kind of seem to be going down again in luminosity. So there is none of them that would go up. But it was very interesting that we analyzed also their infrared excesses, and we took a low resolution spectra. And most of these systems actually displayed strong excess here, for example, or here in the mid-infrared, which shows that there is warm dust around the system, which is likely located in an accretion disk or decretion disk. And then there is H alpha showing that like there is an ionizing source, which is recombining. So the cool stuff is that actually we predicted not a luminous red nova, but an X-ray binary outburst. So one of our best candidates that was actually going up and up was these objects where you can see the light curve. And we discovered it here. We took a spectrum. We weren't sure that it would be like really a luminous red nova, but then a bit later we detected, we saw this ATL that actually said that MAXI detected a hard X-ray transient, and it was a new BE X-ray binary, which was previously unknown. So actually we predicted the outburst of this X-ray binary while looking for luminous red nova. So this is cool, we can actually use this method to maybe find more of these, future transients. So then when we finally extract all the angular momentum from the binary, then the coalescence happens. So luminous red nova here are good objects to study what physics are important to unbind the envelope, right? So as I mentioned previously, we have the energy of the binary, and several works explored through hydro simulations how this energy would be transferred into ejecting the envelope. And one of these examples is here. So the primary star is this big circle. It's here in the middle. It's a red giant with 100 solar radius. And the companion is this little cross that it's hard to see. And of course, this is a very simplified version because, for example, many works ignore any previous mass transfer, any disks, and they just place the companion on top of the envelope and let the system evolve. But this is still good for illustrative purposes. Yeah, as you can see, the distance between these two stars decreased by a lot. And there is a lot of turbulence, for example, in the ejection. But many works reach the same conclusion. And it's that they could not eject fully the envelope of the binary. So the binary orbital energy was actually not enough to fully eject the envelope. So then next works explore the possibility of extra sources of energy. And it seems that recombination energy in the ejecta is a key ingredient to fully help unbind the envelope. So here you can see the evolution of the ejecta. This is the radius, and this is the ionization fraction of the gas, so for hydrogen, helium, and double ionized helium. And we can see that basically the hydrogen is fully ionized in the core, but then the external layers recombine. But then there is still a push from these internal layers to provide these low energy photons, because they are low energy, but they are still kind of pushing the outer layers from the inside. So same for helium. So basically this recombination energy is low, but it really helps to unbind the full envelope of the binary. And these recent works also use these luminous red nova models to propose recombination energy as the power source for the lasers. So initially I showed that there was this really fast blue peak in the observations, and then we had kind of a very long red peak. So then this works suggest that the first peak is due to release of thermal energy. The ejecta is very hot, there are like kind of shocks. The secondary kind of maybe plunges into the envelope. So then there is like a very hot ejected gas, which quickly cools down, and there's the peaks ends. But then these successive layers, which become kind of neutral, and they are like moving inwards, each layer provides a little bit of energy, a little bit of energy. So the sum up of all layers of this recombination in the ejecta actually power this plateau. So similar like type 2 supernova. But then there is like a bit of flaw, and it's because if we look at more massive donors, for example, there are these couple of systems. This is the donor mass, the total mass of the star, and this is the ejecta mass, and this line is 1-to-1. So basically, in order to explain their energies, we see that the ejecta mass in those objects needed to power the light curve needs to be higher than the donor mass. This makes us think that there is something missing in this model, because we cannot eject more than we initially have. And therefore, we need shocks. So these are complementary models that also explain the emission in luminous red nova. And is that if we had, as I described before, this disk, which generates from L2 mass loss, this fast ejecta will also crash into this disk, and it will generate shocks, which can provide initial source of energy for these transients. And this is important as well, because if we have shocks and if we have this crash, then basically the fast ejecta is likely going to be funneled towards the polar regions of the binary, because this kind of this could prevent of the ejecta of going sideways. So we finally will have this kind of hourglass configuration. So in this case, they also describe as the fast peak of a cooling envelope, and the secondary peaks are powered by these kind of shocks of this fast ejecta crashing into the slow precursor wind. So the cool thing is, like, as long as we have more and more of this transients, we have more observations, we can use these models to infer the ejecta masses in these objects. And if we have the archival information on the progenitor stars, we know more or less the mass of the stars and the mass transfer history. So we can constrain whether it was a full merger or ejection, and constrain what kind of mass ratio would be consistent with that binary location. And yet another thing is that we see that there is a strong correlation between the mass of the star and the absolute magnitude of the outburst. So this relation was first proposed in 2014, but then I expanded it with newly discovered objects. And well, this is kind of rotated, sorry about that. This is peak and progenitor mass, and this is the other way around. But you can see there's a strong correlation between how bright this luminous red nova is at peak with the estimated mass of the progenitor. And this, of course, kind of makes sense because more massive progenitor will have more massive envelopes that when they recombine, they will generate higher luminosity transients. So as I mentioned before, we have this disk. And this disk is important as well because this determines how the ejecta will look like ages and millennia after the actual event has happened, because it will create this hourglass structure, and then some dust will form in this ejecta. So we also want to study, for example, how this remnant evolves, and how we can make the connection with this remnant with other objects that we see that have kind of very similar morphologies, such as, for example, planetary nebula. So then we can use for that different domains. So we can use the opticals to study this precursor phase and the outburst itself, but then we can go to the near infrared, because as you can see, the optical outburst is very short, but then near infrared and mid infrared, this was Spitzer, but now we have JWST. We see that these objects, they last for many years in a bright state, meaning that there is a lot of dust formation, there is a lot of warm dust, and it's very interesting to study this dust formation using these objects. For example, this was the Luminous Red Nova in M31, and we can see that the dust temperature decreases with time. So after like 3.5 years, the dust has cooled down by like nearly 1,000 degrees. And there is this also the optical depth of these shells of the gas also have decreased, increased a lot, showing that there is a lot of dust forming the system, which we can also estimate from the SCD. And then we can compare this with our progenitor models and with our, for example, outburst models to see that all the information, all the pieces are consistent with each other. So for some lucky cases, such as this V8 Mon, the red nova that we saw with the echo, or these other V4332 Sagittarius, they are galactic luminous red nova. So actually there were some studies with ALMA by Tomek Kamiński, who is in Torun Observatory. So basically he could resolve using ALMA the remnants of these galactic luminous red nova. And what we see is that indeed their morphologies resemble this hourglass structure that we expected, from the existence of a disk and ejecta funnel towards the poles. So this also is an evidence that disks are common between these luminous red nova. So the final project that we can do is also to estimate the rates of this luminous red nova. And this is something that we did using the Zwicky transient facility. So basically we selected all these, if you remember the banana shape, so we selected all these transients which were in this luminosity gap in between novae and supernova, and we classified everything we could, so about 80% completeness. And using this spectra, if we saw molecular absorption forming later in the spectra, that meant it's a cold photosphere corresponding to one of these mergers, so it was considered mergers. So then we compiled several of these light curves and computed some template light curves, which we used to re-simulate the ZTF survey up to that date to estimate the rate of these objects. So if we put that into context, the first work that estimated the rates was Kochanek et al. 2014. And it actually was very optimistic work that showed that, we could have like, 1 in 1,000 per megaparsec per year. But then new works based on predicted binary population synthesis said that, okay, like much higher system should be less common. But then what we saw was something in the middle. So the rates that we derived for these objects were something in between. And this is very exciting because likely it's related to both the physics of the, how we treat the common envelope. And this is related to this common envelope formalism that I showed you at the beginning. So that means that something is not right, and we need to improve that. And also there is a discrepancy probably in the emission models. So if this work only used the recombination luminosity, likely the shocks also play a role, and that's why we have an enhance in these like higher mass objects. So this is all new questions and new ground to explore. So the future steps is to, of course, keep using ZTF, but there is also new surveys, for example, Winter, which is starting in Palomar, which is in the near infrared. And this is very exciting because we can think that all these massive objects that we saw until now, all their progenitors were in this Hertzsprung gap, which means that they were mergers. So then the next question is, why haven't we seen any full common envelope ejections? And the answer is that perhaps they are infrared only transients. Because, you know, when you enter the envelope of red supergiant, kind of the spiraling, it's very slow. So likely you are going to be obscured by the same envelope, you know, at the time you merge. So it's going to be an infrared only transients. And that's why these near infrared searches are so exciting. And from the south, of course, we just started Black Gem, which is very exciting. And it's even more exciting because Black Gem has a specific targeted service to galaxies which have HST data, which are located closer than 15 megaparsecs. So Luminous Red Nova are low luminosity transients, so we will catch them only in our local universe, but especially if we look at galaxies that already have HST data, we will be able to actually study their progenitors 100% because all massive stars will be detected in those HST images. And of course, when LST stars, LST will also detect both progenitors, precursors, and outbursts for these transients. So it's a very exciting time to be. So this is a bit of my vision now. So this is what we have now. Now optical surveys are only able to detect this really quick outburst and peak. And then, you know, the optical data disappears. So basically, we're only able to study kind of the peak of the iceberg of luminous red nova. But we are in an era that we are going to enter kind of a 360-degree to look at observational properties of luminous red nova, because something with like HST or LSST itself, we will be able to see first the progenitor system, so we can model it and see what kind of configuration is. Then we will see this precursor, and with cadence, with good cadence in LSST and colors, likely we'll be able to derive this period, you know, if it's an eclipsing binary. So we'll be able to study both the evolution of the system and the decreasing period. Then we will, of course, to study this outburst and all the property changes during the optical outburst. And then we have also JWST, which will allow us to study these objects at a later time. And well, I need to mention that with some of my collaborators, we actually got time to study for luminous red nova with double JWST, which is very exciting. So yeah, my conclusions about this is the common envelope is a very critical phase in binaries, which create a large amount of exciting astrophysical phenomena, but there is still poorly understood because physics are very complex, so we need to treat each part separately. But now we are in this observational era, which observations are possible to connect all the pieces. So my project, which is the ERC starting grant, which I have here in Barcelona, it's called CET3PO, which means common envelope transients, progenitors, precursors, and properties of their outbursts. So basically the aim is to first to study the progenitors, also detect the increase in this precursor level, to study how this unstable mass transferring is happening from L2, and also study the outburst itself and put all this together with also the remnant masses and dust. So finally, also luminous red nova rates will allow us to test these prescriptions for common envelope that we are using in binary population synthesis, and hopefully will help us to apply this to other fields such as gravitational waves. Thank you very much.
Thank you. Thank you, Nadia. Questions? I have one, of course, related to Gaia. One at least question is related to Gaia, which ones I have. So Gaia alerts, you've been involved in that. So have we seen any of these luminous red novae, or?
Yes, it's a shame, you know, because I was part of the Gaia team when I started working on these luminous red nova, this one here. But it was not discovered by Gaia. You know, there is like one data point which is crucial here, and I could not put it in the plot because the data was not public. So I'm a bit upset about that, because that was like a, you know, great data that only Gaia had, because it was really close to the sun, you know, and they only could start observing it here, but Gaia could see it earlier. And it was like a very important data point, but because it was not discovered by Gaia, the light curve is not public. So, you know, they told me, oh, you need to wait for the end of Gaia to actually get the light curve. Like, oh my God. So
right. That was the only one which.
Yeah, no, another one. Yeah. This 2018 BW also had Gaia data actually. So that was really nice. Yeah.
Right. And then you mentioned some BE stars. So we see a lot of these in Gaia, right? Are they any useful?
Well, I think, I mean, useful for, I mean, yeah, like now with a student of mine, we have a project which actually take all the emission line stars from Gaia and analyze their time variability, their light curves, and also their infrared excess. And we found like several very exciting objects actually. So this is very cool. Like some of them are not known at all. You know, they are not in Simba, they are not anywhere. And they show like kind of crazy light curve on they're eclipsing binaries, you know. So it's very cool because they have H alpha, meaning that there is something exciting and recombining. They have excess, meaning they have disks. So, you know, maybe some of them will actually blow up as Luminous Red Nova very, very soon.
Okay. Nada? Well, you don't have to come forward because, well, unless you're seeing the camera.
Thank you so much. I just want to make sure that I properly understand this, because I've seen this, well, I've seen that I have this issue from before. So the progenitor of Luminous Red Nova is always a binary system, right?
Yes,
so
correct.
I've seen it mentioned progenitor or progenitors, and I was never sure if, you know, if it's a binary. It always has to be binary system, right?
Yeah.
Okay. So sorry, I just
yeah, no, it's a binary system or a binary star. Yeah, so
okay.
Yeah, so it's a single progenitor.
I mean, normally we refer to the primary star, you know, because the star has grown so much, it generally really outshines any kind of main sequence companion. So then most of the inference you can do is only about the primary star and the mass ratio.
Hello?
Very interesting results. I have two questions. What determines the time scale of the event? Maybe I missed it.
The timescales for...
You mean the duration of the event, of the flare?
Yeah. Okay, well, yeah, let me show you the here. Yeah, so here you have days since the first peak. So basically there is a strong correlation between the peak luminosity, but also duration versus progenitor mass. So smaller stars have wimpier outbursts, you know, which are fainter and quicker. So they can last as, this was V1309 SCO, it lasted less than 50 days. But some objects have like 18 solar masses or more. They are seen up to a year. So, you know, it also depends on if you have these extra shocks, then that can lighten the light course for a bit longer. So I would say between a couple of months and a year. In the optical. In the infrared, it's kind of a very long story.
Okay, I will just add that Paweł Pietrukowicz, who asked the question, he actually looked for these decreasing period objects in the entire OGLE database, and I think the outcome was 0, right? So this is an unpublished, very interesting result. Have you published it? Sorry. Sorry.
The second question I have.
Go ahead.
Because in some light curves, there is this third peak, right? Is it this shock? Just to be sure.
Well, these gray things, these models. I don't know if you refer to this.
For example, TK Bull has 3 peaks, right?
Oh, right. Yeah. V83 Mon as well. Yeah. So I cannot say, yeah, I think it's like several mass ejections. So maybe it related to the dynamics of the secondary inside of the envelope. I think V838 also was a main sequence star. So maybe the ejecta process was slightly different for yellow supergiants. And I think CK Wool was a red supergiant, if I'm not mistaken. It was already an evolved star, so it was not a compact main sequence or yellow giant.
Okay.
So CK Wool was observed in the 17th century, so we didn't have CCDs back then. So.
And then, yes, you mentioned a couple of times, if we were lucky, we would have some archival data. So how can you help the luck? And I see that BlackGen is using the luck, right? So they target the HST monitored galaxies, but in the Milky Way, can you do something now so that then when something explodes, you have the data? Is Gaia good enough?
Yeah, well, Gaia is good, but not very good for weird objects, right? Gaia, every time that there is like an interesting target and you go there, Gaia says, Normally the parallax is not good because, they don't have common SCDs, right? They are stars which are not normal. So you cannot model them with a normal main sequence star because they don't fit. So then all the estimations are pretty wrong.
Well, but then I think the final data set could be helpful. If they are visible in Gaia, then eventually something can be said about them, right?
Yeah, so that's what we did, for example, with Harry, that we tried to look for things that evolved with time, which would reveal this kind of, slow increase in the light curve. Some light curves went up, we were very excited, but they went down again. So yeah, I think you can try to predict in many ways. One of them is the variability. And of course, the location in the Hertzsprung gap, because all those stars, if they're real, not red and blue stars, but they are real Hertzsprung gap, they should experience some mass transfer if there is a companion. And yeah, that's why we approach the problem first through time variability. And now, as we saw that nearly everything had an infrared I excess and H alpha excess, well, these H alpha emission lines. Now we took the Gaia data, which has emission lines from Gaia BPRP spectra, and we are studying these objects more in detail. So yeah, we have a few candidates also in external galaxies, which are yellow supergiants, and they also show H alpha lines. So we are going to study them further to see kind of what stage, evolutionary stage they are, and if they're good or bad candidates, because we need to learn a lot about this if we want to hunt them in LSST data, because this is going to be like a huge monster of alerts, millions per night. So you need to be really clever about which ones you want to select.
That's right. That's a very good conclusion. So thank you very much, Nadia. Let's thank our speaker again. And thank you all for coming. Thanks. Stop this.